Добрий день. Good day, dear students. Today is lecture 15. We start our lecture by interchangeably standardization and technical measurement. The name of our lecture, the theme of our lecture, control of geometrical parameters of typical parts connections. Write down to your notes the theme of our lecture and the plan. Item 15.1 Control of parameters of smooth joint parts. Control of parameters of smooth joint parts. Item number 2, 15.2 Control of thread parameters. Control or inspection of gate joint parts. It's 15.3. Inspection of gate joint parts. Next item, 15.4. Inspection of spline joint elements. Inspection of spline joint elements. Control of geoaccuracy parameters. Control of geoaccuracy parameters. Control of surface roughness of parts. It's 15.6. Control of surface roughness of parts. And item number 7, selecting a measuring instrument for monitoring the geometric parameters of parts. And we start item 15.1, control of parameters of smooth joint parts. The values of geometric parameters of products are specified during their design, usually in numerical form and indicated on the drawings. During the manufacturing process of products, it is necessary to monitor the compliance of the actual value of these parameters with the value established in the technical documentation. Most geometric parameters are numerical values of linear and angular quantities or are estimated through them. These numerical values are called dimensions. And the control process is called dimensional control. Please write down to your notes what is dimensions and what is dimensional control. Thus, the purpose of dimensional control is to compare the actual geometric parameters of products expressed in terms of dimensions with the values of the parameters that were determined during the design of the product. Control is carried out by measurements. with the expression of a parameter in numerical form or comparing them with a measure of measuring surfaces of instruments configured according to the measure. Control parameters of parts. Linear dimensions, lengths, heights, depths, clearances or gaps, distances, diameters, etc. Angular dimensions, angles between planes, axes, angles of cones, etc. And deviation of the shape and arrangement of surfaces from cylindricity, plane, etc. From cylindricity, plane, etc. So, please write down to your notes control parameters of parts. Then deviation of the location of surfaces from parallelism, perpendicularity, etc. and surface roughness. Control of parameters of smooth joint parts. It's item number 1. 15.1. Control of parameters of smooth joint parts. The geometric and dimensional parameters of parts of smooth joints in mechanical engineering are controlled by universal measuring instruments using different measurement methods. Control of linear dimensions. So the geometric and dimensional parameters of parts of smooth joints in mechanical engineering are controlled by universal measuring instruments using different measurement methods. To control the linear dimensions of the external and internal surfaces of parts, all types of mechanical devices and instruments are used, as well as optical, pneumatic, electric instruments, and coordinate measuring machines. In this case, various devices can be used to facilitate access to the controlled surface or to fix the position of the measuring instrument relative to the part. It's tripods, racks, special devices. Devices for adjusting instruments to a given size are also used when performing measurements using the relative method. It was control of linear dimensions. Measuring angles. Objects of angular measurements in mechanical engineering are numerous and diverse. This leads to the need to use various measuring instruments varying in accuracy, measurement limits, performance, and purpose. The most important feature by which measuring instruments for angles and cones are classified is the type of measure with which the measured angle is compared. The first group includes prototypes of products in the form of angular measures. The second group of measuring instruments combines instruments and devices with the help of which the measured angle is compared with the corresponding values of the geometric circular of arc, sector, scale built into the device. The third group of means, trigonometric, differs in that the measure with which the measured product is compared is the angle of a right triangle. The two sides of this angle are reproduced or measured by means and methods of linear measurements. The most common means of measuring this group are sine and tangent devices. Instruments of mass use for machine parts that implement the geometric scheme for measuring angle are inclinometers, like in figure 15.1. You can see the figure 15.1 measuring angles with a protractor. It's protractor and universal. The angle between the surfaces of the part can be determined by comparing the angle with the angle of the standard measure, like in figure 15.2. If the angle of the part differs from the angle of the measure, then the repeatance of the indicator will differ from the reading when the measure is set to a certain value. When checking angles, corner templates with an angle equal to the angle of the part are also used as measuring tools. And in most cases, the part is adjusted to a template without clearance. Metal squares with a working angle of 90 degrees are used to check the mutual perpendicularity of the planes of products, like in figure 15.3, with angle 90 degrees. It's metal square. Measuring an angle using a square and final measures length. First length and second length. The clearance can be observed both at the end of the side of the square. The angle of the product is greater than the angle of the square. And at the top of the angle, if the angle of the product is less than the angle of the square. For clearances or gaps of 20 microns or more, probes can be used. Finite length, final length measures are used to evaluate clearances from 5 to 20 micrometers. When checking angles with contact devices, a stand with a device is placed on the plate, the axis of which is horizontal, and there is a stop, like in figure 15.4. You can see the contact device. Stand with the device is placed on the plate, the axis of which is horizontal, and there is a stop. It's the plate. And it's square. The difference in the readings obtained when the device comes into contact with the square and the product is related to the distance A between the axis of the measuring tip and the working surface of the plate is taken as the deviation of the angle of the product. Typical examples of the implementation of trigonometric methods of measuring angles are measurements using so-called sine rulers. You can see on the figure 15.5 measuring the angle with a sine ruler. Position number 1 is sine bar. 2 and 5 rollers. Roller 1 and roller 2 rollers. Position number 3, block of finite length measures. Position number 4, calibration plate. Position number 6, emphasis. 7, measured part. you can see the measured part with the angles. Measured part and stand with indicator 8. It's stand with indicator. When measuring, the sign ruler is installed with rollers on the verification plate 4. You can see this plate, verification plate 4. A block of gauge blocks of such size is placed under one of the rollers. So that the measuring plane of the sign ruler is located at a given angle of the verification plate. The part to be measured is installed on the measuring plane of the ruler. It's measuring plane of the ruler. So that it is pressed against the stops 6. An indicator stand with indicator 8 is placed on the test plate next to the sign ruler. For various designs of sign rulers, distance 1 can be 100 or 20 or 200. The two-ball method is widely used to measure the angles of internal cones. The essence of this method is that two precisely manufactured balls of different diameters are sequentially placed into the conical hole. Let's look on the next figure. We can see this method on the figure 15.6. 15.6. So, the essence of this method is two precisely manufactured balls. It's first ball and second ball of different diameters are sequentially placed into the conical hole. It's conical hole. Of the part, and the distances h are measured using an indicator. You can see small h and big H. Big H the distance between small ball and surface, outer surface of the part. And small h is distance between big ball and outer surfaces of the part. It's small h. So, these distances h are measured using the indicator. Or micrometric or depth gauge. And A between the balls and one base surface, like in figure 15.6. Before placing the balls, their diameters are also measured using a micrometer. Based on the rulers of the measuring performed, the sine of half the actual angle of the cone is calculated. To simultaneously control the dimensions of the cone, external and internal, cone gauges are used, manufactured as a set, like in figure 15.7. Let's look at the figure 15.7. You can see in this slide, figure 15.7, set of gauges for testing conical holes and shafts. A, it's plug gauge, and B, it's bushing gauge. Bushing gauge. So inspection of products by gauges is complex since not only the angle of the cone is checked, but also its diameter in the design section by the position of the gauge relative to the product along the axis. For these purpose, there are two limiting lines on the surface of the caliber or gauge, respectively a ledge on the bushing gauge. The cone angle of the part is checked by the contact of the gauge surface with the surface of the part being tested. Bushing gauges are bushing with internal cones, the outer cylindrical surface of which has knurling. For angular measurements and dividing work when marking and processing parts, optical dividing heads are used. Control of surface location deviations. To monitor deviations in the location of the surfaces of parts, indicator measuring instruments are used. Typical schemes for measuring deviations of surface locations are shown in figure 15.8, 15.11. First, figure 15.8, schemes for monitoring deviations from parallelism of planes. Location deviations from parallelism, perpendicularity, slope, etc., are determined based on the location of nearby straight lines of planes. The latter are the planes of the test plates, of which the parts are installed, and the planes of the test rulers, squares and special mandrels installed on the parts. So it's a plate and special instrument to determine the parallelism. First, it's measuring ruler. Second, measuring head figure. When measuring deviations from parallelism or misalignment of shaft axis, it should be remembered that the axis itself is immaterial. Therefore, measurements are made relative to the genetics of the real surface of the part itself, the shaft, figure 15.9. Sign the axis of the center holes. Let's see all. Figure 15.9. A. Since the axis of the center holes of the shaft is the main technological basis for processing, when testing, the installation of the shaft on the center holes is often used. (15.9a). So you can see the axle and installation in the cones. When checking the deviations of the actuating surface of the shaft relative to the bearing journals, the shaft is mounted with these journals on prisms. You can see first prism and second prism. What is the prism? Prism. There are the prism, and it's a shaft. First prism and second prism. The shaft is mounted with these journals on prism, and the indicator determines the degree of deviation when tuning the shaft a full turn. We tune the shaft a full turn to 360 degrees, and we measure the deviation using the head, indicator head. When manufacturing parts such as bushings, it is necessary to ensure precise coaxial arrangement of the outer and inner cylindrical surfaces. Monitoring deviations from the alignment of these surfaces is not often carried out according to the scheme with the installation of a bushing on a control mandrel, with the help of which the axis of the base hole is materialized. By placing an indicator with a stand next to the tool plate, you can record the degree of misalignment of the outer and inner surfaces relative to the base hole. The fit of the bushing on the mandrel should allow it to rotate easily, but with minimal clearance in the fit. To control the deviation from the perpendicularity of the end of the base hole of its axis, a device is used, which with its rod enters the main hole of the body with a minimum clearance and is based on the end with a flange with 3 supports. Like in figure 15.10. Figure 15.10 scheme for monitoring deviations from perpendicularity of the end base hole. You can see the hole in the bushings and perpendicularity of the hole and this surface. Indicator head. When manufacturing body parts, problems arise with determining the accuracy of the location of numerous holes and planes. Since the axes of the holes are not material, their position is materialized by inserting precisely fitted mandrels or bushings into the holes. Figure 15.11. You can see special mandrel that installed to the holes, and two stands with indicator heads. It's measuring instruments. It's schemes for monitoring the location of surfaces of the body parts. Please write down to your notes the figures 15.10 and 15.11 and 15.9. Do it now. And we are continue. Next item of our lecture, control using gauges. For today is last item, and we are continue on the next lesson, other items of our lecture. So, control using gauges. In mechanical engineering, the so-called alternative method of monitoring the suitability of products is widely used. It allows you to separate products into suitable and defective. When alternatively checking the geometric parameters of products, gauges are most often used. Gauges are scaleless measuring instruments for checking linear dimensions, angles, shapes, and relative position of surfaces. With the help of boundary gauges, they determine not the numerical value of the controlled parameter, but find out whether this parameter goes beyond the limit values or is between two acceptable ones. According to their purpose, gauges are divided into working gauges, intended for checking parts by workers, and control gauges for checking working gauges during their manufacture and operation. During inspection, a part is considered suitable if the passable side of the gauge, go side, it's go, side, it's not go, excuse me. No, go side, and it's go side. It's not go side. And go side. So its go passes under the force approximately equal to the mass of the gauge, and the non-passable side, non-go side of the gauge, no go, does not pass along the controlled surface of the part. If the go does not pass, the part is classified as a part with a correctable defect. If it does not pass, the part is classified as defective with an irreplaceable defect. Irreparable defect. Irreparable defect. Defect that we can't repair. There are several types of gauges. Smooth gauge, staples, serve to control the lengths and diameters of outer surfaces. They can be one-sided and two-sided, single limit and two-sided limit. Single limit gauges so you can see general VF of gauges. A, it's one-sided, double-sided one side and second side, double-sided. It's B, and C, adjustable. It's go side and no go side. Adjustable clamps, adjustable gauges are also used, which can be adjusted to different sizes, which allows you to compensate for wear and use one clamp to measure different sizes within a certain interval. But adjustable gauges compared to rigid ones have less accuracy and relatability, so they are more often used to control products with 8 IT grades. Smooth plug gauges like in figure 15.15, smooth plug gauges. General VF of plug gauges, it's one-sided and double-sided. For example, it's go side and no go side. Serve to control holes. We use these plug gauges to control holes. Structurally, they are made in the form of a handle and a working part. The working part can be made together with the handle on or in the form of inserts and attachments. Plug gauges can be single-sided or double-sided. One-sided ones are made possible or impossible, go or not go. For smooth plug gauges, the go side has the smallest limit size. It must go into the hole. And the non-go side, it's go side and no-go side. No-go side has the largest limit size. It must not go into the hole. Smooth gauges allow you to control liner dimensions from 0.1 millimeters to 3,150 millimeters. As the dimensions increase, the control error increases due to increase in elastic deformations of the gauges. When designing boundary gauges for smooth, threaded and other parts, it is necessary to comply with the principle of similarity, Taylor's principle, according to which the pass-through gauges, go side gauges, in their shape should be a prototype of the modern parts with a length equal to the length of the connection. That is, for shafts have the shape of rings. This is necessary in order to control the dimensions along the entire length of the connection, taking into account the errors in the shape of the paths. Non-go gauges should have a short gauge length and close to point contact to check size only. However, in practice, it is necessary to divide from the Taylor principle due to the inconvenience of control. For example, with a pass ring, since this requires repeated removal of the part fixed in the centers of the machine. Therefore, instead of pass-through rings, multiple inspections are used with pass-through brackets with wide measuring surfaces. Gauges for monitoring the depths and heights of ledges. These gauges, like in figure 15.16, are structurally stepped plates of one shape or another. Such gauges determine the suitability of the product in the presence of a clearance between the corresponding planes of the gauge and the product of the gauge and the product. Instead of pass or go and fail sides and not go sides, these gauges have sides corresponding to the largest and smallest maximum dimensions of the product. The main control methods are the following: light slit, approaching and along the risks. So that's the last slide for today. Our lecture is finished. Have you questions? If you have questions, please write down it to our Telegram group, write down to our forum. Now you need to write down this figure 15.16 to your notes. You have the time, and after that, our lecture will be finished. Dear students, our lecture is finished. So goodbye. See you next time, the next week. Have a nice day.